Hi, my name Nadia Sayed Ahmed Sayed, fourth level chemistry department, prepared by Sra Ahmed, Salma Tariq, Marina Tariq, Marina Faiz, Marwa Abdelal, Maryam Karam, Nariman Khalid, under supervision Professor Dr. Samy elwafa. And we will study today X-ray single crystal. Comparison between X-ray diffraction (XRD) and X-ray single crystal can be used to analyze the atomic or molecular structure of materials. The technique is compatible with various solid materials, including crystalline materials or powders. The structural information recovered from XRD methods is sufficiently sensitive to small differences in lattice spacing that can be used to distinguish elementally identical and structurally similar polymorphs. Powder X-ray diffraction is used on microcrystalline powder samples. Powder XRD can be relatively quick compared to X-ray single crystal due to the significantly reduced difficulty in the sample preparation step. When preparing a sample for powder XRD, the particle size should be as homogeneous as possible and less than 10 micrometer in diameter. All the microcrystals will be randomly oriented, but too small particle size or too much variation in the particle size in a sample can lead to the broadening of the peak structures and potentially complicate the structural assignments. What is X-ray single crystal? X-ray single crystal diffraction differs from powder diffraction in sample preparation and equipment required. Powder samples tend to give rise to continuous diffraction rings. This can result in ambiguity in the data interpretation and the need for trying different fittings to the data to interpret the final structures. In X-ray single crystal, single discrete diffraction peaks are observed. Using a crystal X-ray diffractometer, peak positions can be transformed into a series of coordinates to recover the underlying crystal lattice dimensions or crystal orientations of the sample of interest. The interpretation of single crystal diffraction is much less ambiguous than powder diffraction methods, but the challenge in this experiment is to prepare the single crystal samples, which can often be a highly laborious and time-consuming process. Although the crystal structure information is more straightforward to interpret, the spatial properties of a single crystal may not necessarily be reflective of the bulk solid. This can also mean that measurements of stress and strain on the crystal may not translate well to describing the bulk properties of interest for a given application. Introduction: the scattering of radiation with wavelengths of about 100 pm from crystals gives rise to diffraction. The interpretation of the diffraction patterns give: number one, quantitative structural information, and in many cases, the complete molecular or ionic structure. Diffraction is the interference between waves that occurs as a result of an object in their path. X-rays are scattered elastically with no change in energy, by the electrons in atoms, and the diffraction can occur for a periodic array of scattering centers separated by distances similar to the wavelengths of the radiation, about 100 pm, such as exist in crystal. This picture shows Bragg's equation is derived by treating layers of atoms as reflecting planes. X-ray interfere constructively when the additional path length to d sine theta is equal to an integer multiple of the wavelengths. Suppose the scattering is equivalent to reflection from two adjacent parallel planes of atoms separated by a distance d, as seen in the above figure. The angle at which constructive interference occurs to produce a diffraction intensity maximum between waves of wavelengths is given by Bragg's equation. 2d sine theta equal n lambda, where n is an integer, a diffraction pattern with each reflection occurring at an angle theta, corresponding to a different separation of planes of atoms, d in the crystal. Note, crystallographers still generally use the angstrom as a unit of measurement. This unit is convenient because both the lids typically lie between 1 and 3 angstrom, and the X-ray wavelengths used to derive them usually lie between 0.5 and 2.5 angstrom. There are two principal X-ray techniques: the powder method, in which the materials being studied are in polycrystalline form, and single crystal diffraction, in which the sample is a single crystal of dimensions of several tens of micrometers or larger. Single crystal X-ray diffraction and structure analysis. Single crystal X-ray diffraction or X-ray crystallography is an analytical technique in which X-ray methods are employed to determine with certainty the actual arrangement of atoms within a crystalline specimen. Single crystal X-ray diffraction is the most powerful method known for obtaining the atomic arrangement in the solid state. X-ray crystallographic structure determination can be applied to a wide range of size of structures, from very small molecules and simple salts to complex minerals, synthetically prepared inorganic and organometallic complexes, natural products, and biological macromolecules such as proteins and even viruses. The experimental data obtained from these techniques may, after suitable analysis and interpretation, yield important information concerning the composition and structure of the compound. An atom or ion scatters X-ray is proportional to the number of electrons it possesses, and the intensities of the measured diffraction maxima are proportional to the square of that number. Thus, the diffraction pattern produced is characteristic of the positions and the types in terms of their number of electrons of atom present in the crystalline compound, and the measurement of X-ray diffraction angles and intensities provide structural information. Analysis of the X-ray diffraction patterns obtained from single crystals allows the structure of molecules and extended lattice to be determined, although hydrogen atoms are often not located in inorganic compounds. There are two pictures. The first one shows the layout of 4 circle diffractometer, and the second a part of a single crystal X-ray diffraction pattern. This video talk about what is single crystal X-ray diffraction experiment. A crystal is placed in a center of the instrument. The crystals rotated in a beam of X-ray and two-dimensional detector records the signals from the sample from the position and the intensity of these signals. The three-dimensional structure of the sample can be unambiguously determined. Many minerals such as diamond and salts, organic molecules such as sugar and drugs, and salicylic acid appear as small crystals. In these crystals, atoms or ions or molecules arranged in a highly ordered structure, forming a crystal lattice that extends in all three dimensions.
The position of hydrogen atoms can be determined by four inorganic compounds that contain only light atoms. That example less than 18, such as alcohol, but their location in many inorganic compounds that also contain heavy atoms such as 4D and 5D series elements can be difficult or impossible. The problem lies with the small number of electrons. Such a hydrogen atom, just one electron, which is often reduced even further when it forms bond to other atoms. When it make bond with any atoms, okay. Furthermore, as one electron is normally part of a bond of of hydrogen atom, its electron is um, is form one bond. Okay, the X-ray determined position of this electron density is often displayed along the bond direction. The production or this produces bond length shortest compared to the true intermolecular distance. It's very short. Okay. Other techniques such as neutron diffraction can often be applied to determine the position of hydrogen atom in organic compounds. We can know molecular structures by analysis of single crystal of X-ray diffraction, which represented in ORCEP diagram. An example of ORCEP diagram is cisplatinum or cisplatin. When 90% probability of locating the electron density is associated with the atom. This is orbital shape on the left side, thermal ellipsoid plot, and right hand unit cell diagram. Graphical representation of X-ray diffraction technique will explain how single crystal occurs. First step, shine X-ray on the crystal vertical. After that, the crystal becomes dispersed and then assembled in the dispersion pattern. Second step, we observe is to collect the electron density, and we have the atomic model. On left hand, electron density difference map of borodinitropbenzene. On right hand, the reference of axes X, Y, and Z are right-handed, then the length of unit cell is parallel to each axis, alpha and beta and gamma respectively. Graph of X-ray diffraction at photon simulation, then polycrystalline, single crystal. This content of this diagram. X-ray diffraction pattern of single crystal polycrystalline sample and simulation profile of PaCO2 V2. The Miller indices of each peak are represented in this figure. The inset shows a photograph of a single crystal of PaCO2 V2. Any X-ray diffractometer consists of three basic elements. 1. An X-ray tube, 2. A sample holder, and an X-ray detector. X-rays are generated in an X-ray tube by heating a filament to produce electrons, then accelerating the electrons toward target by applying voltage and impact of the electron with the target material. This electron possesses sufficient energy to knock out the inertial electrons of specimen given characteristics X-ray spectra. The basic hardware components of a typical automated single crystal X-ray diffractometer system include: 1. An X-ray source consisting of high stability X-ray generator, copper, molybdenum, or silver, target X-ray tube, tube shielded with associated shutters, attention and safety interlock, a monochromator or X-ray mirror system, and an incident beam collimator. 3 or 4 circle geniometer system that allows the specimen to be precisely oriented in any position while remaining in the X-ray beam. A video camera or for aligning the specimen and indexing crystal faces, and CMOS-based two-dimensional X-ray detector system allow temperature attachment for cooling the specimen during the collection. Microprocessor based interface molecule or module that receive commands from host computer and carries out all real-time instrument control function to drive generator motors, monitor that the detector system open and close the shutter, and monitor collision يعني, content or so on, and safety interlock lock of device. Host computer with a large hard disk, mass storage device, a video monitor, and a keyboard, and diffractometer control programs to control the data, okay, data collection strategy, and to send commands to the microscope. Some definition of X-ray diffraction. The first definition, X-ray scattering techniques. It's our family of non-descriptive, destructive analytical technique which reveal information about crystal structure, chemical composition, and physical property of material and descent. This technique are based on observing the scattering intensity of X-ray beam hitting a sample as a function of incident and scattered angle, polarization, and wavelength or energy. And then X-ray diffraction. X-ray diffraction is a technique or the process by which beam of light or other system of waves is spread out as a result of passing through a narrow aperture or across an edge, typically accompanied by interference between the waveforms produced. Electron backscatter diffraction is sample EPSD is a scanning electron microscopy technique used to study crystallographic structure of the material. Okay, it carried out the scanning electron microscope equipped with an EPSD detector comprising at least phosphorescent screen, a compact lens, and low light camera. Then electron diffraction. Electron diffraction refers to change in the direction of electron beam, okay, due to interaction with some atoms in it or with it. Close to the atoms, the changes are dispersed as Fresnel diffraction. Far away, they are called Fraunhofer diffraction. The resulting mass of the directions of the electrons far from the sample, Fraunhofer diffraction, is called a diffraction pattern. See, for instance, these patterns are similar to X-ray itself and the neutron diffraction pattern, and are used to study the atomic structure of gases, liquid, surface, and bulk solids. Okay, يعني gases, liquids, and bulk solids. Electron diffraction also plays a major role in the construction of images in electron microscopes. Finally, we talk about application of X-ray diffraction and what is future of X-ray diffraction. At first, application of X-ray diffraction, powder X-ray diffraction is popular in pharmaceutical analysis due to the short sample preparation time and the amount of information that can be recovered on the crystalline phases, okay, in the crystalline phases of the substrate. Power-based methods are also widely used in mineralogy for research and industrial applications. First, pharma or medicine applications, and industrial applications, mineralogy applications, so on. This can be used to evaluate material performance and for again annotating specimens of historical interest. What is the future of X-ray diffraction? Powder and single crystal X-ray diffraction methods have become workhorse technique for material and pharmaceutical data collection. While many measurements still benefit from the energy, tunability, and photon does available at advanced light source in infrastructures such as synchrotron. There has been a great proliferation in the number of available labs based on X-ray source. X-ray sources. One area of development for powder and single X-ray crystal XRD is the application of this methodology to new sample types. This includes complex materials such as nanocomposite polymer species and thin film.
MCQ questions on X-ray single crystal. Number 1. In X-ray emission tubes, X-ray is emitted by the acceleration of answer electrons. Number 2. The wavelength of range of X-ray is the answer is 1 nanometer to 0.001 nanometer. Number 3. X-rays aren't used in the answer photocells. Number 4. X-ray is process. Electromagnetic character is true. Number 5. X-ray are produced effectively electrons when they tackle dense metal anode. Number 6. The synchrotron radiation emitted is polarized. The answer is true. Number 7. The celestial source of X-ray is the answer black holes. Number 8. Which of the following diseases can be detected by X-ray? The answer pneumonia. Number 9. X-ray crystallography uses which characteristics of light? The answer diffraction. Number 10. Which phenomena is shown by the given figure? The answer X-ray crystallography. Number 10 is the atomic number of the zirconium, molybdenum, or palladium and tungsten are 40 or 42 or 46 and 50 respectively. The suitable filter for X-ray radiation from molybdenum is the answer palladium. Number 12. X-ray single crystal is used to determine the answer all of the above. 13. X-ray are generated by the answer college tube. Number 14. Collimators used in X-ray diffraction are made up of tungsten metal plates. Number 15. The relationship between minimum wavelength of X-ray radiation generated from a target metal and applied voltage of given by Hunt equation. 16. The useful range of X-ray region for parametrical analysis is 0.01 to 0.1 nanometer. 17. In X-ray powder camera technique, the detector used in photographic film. 18. One of the widely used target material for generation of X-ray spectral line is molybdenum. 19. The X-ray diffraction is based upon Polar's equation. 20. The plot drawn in X-ray diffraction spectra is interatomic distance versus angle. 21. The detector in X-ray diffraction that detects the visible radiation scintillation counter. 22. Which of the following detectors in X-ray diffraction has more resolution proportional counter P? The answer scintillation counter. 23. In gas phase detector in X-ray radiation high voltage is applied in the region of Getter counter region. 25. As the applied voltage increase the minimum wavelength of X-ray radiation from metal, the answer decreases. 26. If the atomic number of copper and molybdenum are 29 and 42 respectively, longer wavelengths of K align is the answer copper. 27. Which one of the following statements about X-ray isn't true? The answer letter C. Due to their wavelength being shorter, this can be used for radar system. 28. X-ray are the answer letter D, not affected by an electric field or magnetic field. 29. A beam of X-ray is constructively scattered in second order from the surface of the crystal at an angle of 30 degrees, and the spacing between layers of atoms in NaCl crystal is 4.5 by 10. The wavelength of X-ray is 2.25 by 10 power negative 10 meters.